Thank you. It's a great pleasure to be back here. I actually gave a talk at Rust NYC about 3 years ago on a different project that I work on called Cargo Semver Checks. It's a library for semantic versioning of linting, essentially. It's something that I'm sort of much better known for in the Rust community. I wear many hats in the Rust space. Today I'm here with my employer hat on, so I work at OpenAI, and that's what I'm talking about in this talk. But if you bump into me in the hallway or at the bar later, feel free to ask. So this talk is about a case study that I personally was involved in. This is code that I wrote, things that I shipped together with the wonderful people on my team and more broadly at the company. So I'm super excited to tell you about it. But before we dive in, I want to just get a sense of the room. Who here writes Rust at least somewhat often? Awesome. And who here has written unsafe Rust? Nice. We have a good number of people. Who here has used Miri? Okay, awesome. So just to bring us all on the same page, Rust programming language. This is the meetup, kind of a core concept. Welcome to Rust NYC if it's your first time. Unsafe Rust is a special mode that doesn't allow you to break the rules of Rust, but instead allows you to pinky swear to the compiler that you will uphold all of the rules manually. So it's kind of like full-on training wheels are off mode. And if you mess up, you're going to spend 3 months debugging whatever went wrong because you kind of were asking for it, right? So it's very much high stakes, but it does allow you to squeeze a couple of percent more performance in some places, and so that could be quite worth it. But it also is not a thing that you do every day. So this is a talk about making unsafe Rust safer, because at the end of the day, at the scale that we work at, a couple of percent of performance is actually a huge deal. And because of the nature of what we work on, we get way more than a couple of percent by using unsafe in the manner that I'm going to show you. So the TLDR of this talk is this. I'm going to start right with the bottom line. With Codex, which is OpenAI's coding and general work harness, we can subject our work to 100 times more scrutiny than ever before. And that is how we end up shipping faster. Because not having bugs that get deployed to production means that you move more quickly. We catch more bugs sooner. That's huge. So this talk has 3 parts. I want to walk you through each of them. So this is going to be the why, the what, and the how. The why is about convincing you that there is a problem to be solved. Okay, so we're going to talk about why this is very expensive and very serious. Won't go away. The what is what actually we shipped. How do we solve this very expensive? And then the how is how we actually managed to roll this out in just a matter of a couple of weeks. So he can vouch for this actually shipping and being a of all of the new models that you're in love with using as much. So let's dive right in. Let's talk about the why. Before we dive in, I want to just bring everyone on the same page about what model training looks like. So the stuff that we work on is part of the key foundation for a training stack, how we make every model happen. And the way training works is roughly like this. You have some number of GPUs, 1 through n. You have some coordinator, and the coordinator makes sure that training happens in a sequence of steps. So it tells every GPU, hey, load the next chunk of data, do some training, all the GPUs talk to each other or whatever. And then they all say, okay, we're done with this step. And the coordinator says, okay, go ahead with the next step. This is massively simplified. In the real world, there are a lot more moving pieces, but this is good enough for the purpose. And because you can imagine that you have millions of these training steps, you can't afford to just YOLO run 1,000,000 steps and then if something goes wrong, who cares, right? Just start from scratch. So what you do is you checkpoint every so often. So every so often, instead of moving on to the next step, you say, hey, let's just save the state in the entire system. If something goes pear-shaped, when something goes pear-shaped, we have something to recover to. All right, so we take the checkpoints, and then when inevitably something bad happens to the training, we say, okay, that step didn't pan out, just recover to the most recent checkpoint. This isn't free, right? This is time that we could have spent training. We're clearly not training. But not only that, we're paying for the recovery, but we're also rewinding some number of steps because we don't checkpoint after every step. That would be ludicrously expensive. And so we have to fall back to redoing all of the steps since the most recent checkpoint, right? So there's pressure to checkpoint as often as you possibly can, which is a pressure in performance. There's also pressure on recovering as quickly as you can because that is time that you're not training, okay? Here's the most important and most difficult part of all of this. That recovery from a checkpoint isn't done until all of the GPUs are on board, okay? That is going to come back to bite us in just a hot second. I just want to talk about the cost of outages. If you just threw everything I just described at a cluster and went, okay, let's just train, we don't have to worry too much. Outages will cost you about n to the power $2.25. Just like unavoidable things just going pear-shaped when you least expect it. Okay? I'm more than happy to walk you through the math on how I derived this number, but it's a staggeringly large number. Like if you 10x the number of GPUs, you spend almost 200 times more dollars just like waiting for the GPUs to come back online and resume training. So you haven't done anything, right? That's terrifying. The TLDR of how this happens is in 4 things. One is that you have more GPUs, so every wall clock second is more expensive. 2, you have a bigger system, so there are more things to fail, so that when things fail, the same number of wall clock seconds is a lot more money. And then there are 2 things that are directly related to storage performance. One is that however much performance you get out of your storage system, that's how often you can checkpoint. And then every time you recover from a checkpoint, you lose some number of steps. So the more often you checkpoint, the less stuff you lose. That becomes more difficult with a bigger system. There's more stuff to checkpoint, right? And similarly, the time to recover to more GPUs is generally more, even if you just scale everything horizontally with a bigger system. So your recovery is also more expensive. You can see that these numbers tends to multiply much more than they add, and that's how you end up with these high recovery speeds. So that's how this becomes very, very expensive very quickly. In case you're wondering, I have N on the slide over there. Those like things that look like dust on the screen are cars. So that is a very large N that we're working with, and it's getting bigger as we speak. That photo is actually a few months old, and it's a lot bigger even now. So this is a very, very, very expensive problem, okay? Slow code wastes data center seconds. The hourly rate on that would make a high-priced lawyer blush, okay? We cannot ignore that. There's only one thing that's worse, and that's shipping wrong code, because wrong code wastes data center months. Okay? And that is 1,000,000 times worse. So we cannot afford to ship wrong code that we then discover several months down the line after we've been training on a right? That would be ludicrously expensive. So we'd rather take slow than wrong. We're not happy with slow, but the alternative is worse. That's the problem that we're solving. So how do we solve it? Remember how I said that recovery isn't done until all the GPUs are done? This is pretty humbling. It means that every percentile that I've ever cared about at every previous job doesn't matter. P50 doesn't matter. That's the median performance of your system. Nobody cares. The 99th percentile doesn't matter. Nobody cares. All the GPUs, P100 or bust. That is brutal. Optimizing for the absolute latest tail is brutal in your system. Here's a realistic but hypothetical example. So these are not real measurements. I just plotted what a latency distribution would look like. This is a system where the median response time is 50 milliseconds. Sounds awesome. And the P95 is like 200-ish milliseconds, and that's also awesome. And the P99 is like 700-ish milliseconds. That's still super acceptable. But I've extended this line to P999 and P49s and P59s. And these are real numbers that we have to care about, because if you have 1,000 GPUs, then P100 is about P39s. If you have 10,000 GPUs, it's 4 nines. If you have 100,000 GPUs, it's 5 nines, right? And you can see that this is curving the wrong way. We don't like that, okay? And so how do we deal with this? Well, what we're going to do is called hedging. When a client makes a request to read some data from storage, we're going to see what happens. If the response comes back before P95, awesome. That is a good response, happy with it. If not, we're going to fire a second request for the same data to a different place. And we're just going to bank on one of them returning at some point, right? If neither of them returns, the system is probably overloaded. But if at least one of them returns, we don't really care which one, right? We're just racing the two requests. This is really nice because it caps how much extra work we're doing. We're not doing any more than about 5% extra work, but it has a huge effect on latency. Here's the difference. So the orange line is the same thing, but we hedge after P95. So P50 and P95, same exact behavior. At P95, we just fire off a second request. It's sampled from the same distribution as the original, and we just take whichever one is faster. Okay? And the difference is dramatic, right? It's like factors worth of difference at every step. And also, if you slice the other way, you can see that we essentially end up adding between 1 and 2 nines worth of latency, like percentile, right? So approximately, the P99 over here falls a little bit above the like 3 and the P59s on the orange curve is like roughly where 2 nines fewer is on the blue curve, right? So we've essentially allowed the system to scale to 100 times the size and retain the same, broadly speaking, latency characteristics. This is awesome, right? We should absolutely ship this. Small problem. This is just one facet of the things that the client has to do. It also has to worry about retries. It has to worry about checksums to make sure that all the bytes that got sent actually got received. I got funny stories about that. Ask me later why we need this. We need to actually figure out what P95 is, because how does the client know what is the right point in time in which to retry? We have huge payloads. This is a storage system. We're not just fetching a few kilobytes. So we have to stream those huge payloads because you can't just send 1 gigabyte in one frame, right? That's just not going to happen. Also, the reads might be scatter-gather. They might not be sequential. They might be like, read 4 bytes every 32 bytes. And so you might be holding a very large region of memory in mind, but only writing sort of not sequentially, skipping around a not necessarily predictable way. So the bottom line here, remember we're writing Rust, is like, wait, hang on, like we're writing to a mutable slice of Rust, like, U8, from multiple places concurrently with all of this extra stuff going on. I mean, isn't that like undefined behavior? Like, clearly, right? Like just aliasing straight up, just toss this idea out the window. We can't do this, right? And to be fair, I also thought this, but as it turns out, if you walk a very, very, very fine line, you can pull this off, okay? Pulling the two futures in parallel is undefined behavior because you have two references to the same mutable slice of memory from the same place. Mutable slices, not sync. They're not thread safe. You can't like pull them from two different threads. Undefined behavior. Okay. But if we pull them one at a time from the same thread, that's actually fine. So we can pull them concurrently, not in parallel. So it's okay if the two things are interleaved. They just can't be running at literally the same time. They can just be logically at the same time. Okay? Really fine distinction, matters a heck of a lot. Also, we can't actually give the mutable slice to both futures. If we do this like perform read and then here's the mutable slice, dot await, boom, undefined behavior immediately. Why? Because both futures then take that mutable slice and stick it into the implicit struct that futures have, right? And so all of a sudden, aliasing violation, immediately, this is undefined behavior. Okay, so like, I guess don't do this. Instead, what we're going to need to do is figure out a way to only give futures the mutable slice while they're being pulled, and then when they're not being pulled, just sort of like take it away so that they can't have it, and then we give it to the other future, and then it can get pulled, and it can do its own thing, and then we just like flip-flop between them. Okay, wonderfully, Tokio's async read has a method for exactly this. I've highlighted this like immutable borrow of read buff. Read buff wraps the buffer. This elided lifetime with the underscore over here is the lifetime of our buffer. You can see that the other lifetime isn't named, so the future can't hold on to it. This is all extremely complicated, but technically there is, if you're willing to do a tightrope walk, you can, do it exactly right, and everything in principle could work. So that's only half of the steps, right? We still need to actually manage this exclusive access to the mutable slice. And we have to manage pointers and then turn them into mutable slices at exactly the right moments in time. And we have to pinky swear unsafely that the pointer is actually send because we know some magic that Rust doesn't. and we have to prohibit Tokio spawn so we don't get that parallelism that we didn't want. And we need to drive this like async read, poll read API manually and not rely on all of it. So like this is doable, but it's a heck of a lot of work to get right. And if you don't get it right, I mean, don't make me tap the sign, right? So no pressure, just like you get one shot or else. All right. So let's talk about how we actually made this happen in a couple of weeks. These are so many places where bugs can sneak in, and actually the problem is even worse because remember these other things I talked about? Yeah, we still need to worry about putting all of that code together with the retries and the checksums and the streaming and the non-sequential reads and blah, 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 right? So this is just kind of a lot to even keep in mind, let alone build and implement and test, right? So why is having Codex in the loop a step change for us? I want to argue that that's because there's a huge difference between what's difficult and valuable and what's really time consuming. And we've really managed to find a way to thread the needle and separate these two. This stuff is engineering. We need to design robust systems. We need to think about what the failure modes of our system. This is what gets me out of bed in the morning. Okay. Everything in the other bucket is stuff that is a necessary performance in order to make the engineering be real in the real world. Right? So you might write 200 lines worth of really intense unsafe code and spend 2 days just staring at it and getting it exactly right. And then there's 1,500 lines worth of plumbing just to like get that plugged into all of the right places. And then there's several thousand lines worth of test cases that you want to stick on there. And somebody needs to write the test harness. Okay, let's write the test harness. Who's excited about that? Right? I mean, it's super important to get right, but like that's not the part that I get out of bed for every day. And at the end of the day, cool, we have a 4,000 line PR, which this was. And then now somebody needs to review it. Well, we can't just slap 4,000 lines on their desk and be like, hey, please like check this out over lunch or something, right? We have to split it up into reviewable PRs. So cool. We split it up into a stack of 6 PRs that will each be reasonable to review. But I didn't do that work, right? Code that we want to merge is the code that we want to merge, but Codex actually managed writing the test harness according to what we asked for it and splitting up the complicated 4,000 line PR into a stack of 6 PRs and so on and so on. So give the time consuming bits to Codex and focus on what is truly difficult and valuable. That's one facet of looking at the problem space. The other way is to think about now that you're focusing on these high leverage things and you're passing off the ceremony to Codex, how can you actually change how you work in the first place? I have 3 things to share with you. The first one is something that happened way before we wrote any lines of code for this project that we intended to merge, which is just de-risking it. Like, will this even work? Right? We constructed this like, okay, if you get these 17 things exactly right, then it might just work. Wouldn't it be nice if we had some proof that that actually works end to end before we committed to even spending, weeks of engineering time? With Codex, code is cheap. Hey, Codex, find some prior examples of people using async read, poll read, that API that we want. Let's see how people use it. Let's see if what we're trying to do has already been done. Let's find some prior art to figure out, what are the gotchas that we should avoid? Are there any reasons why we might not be able to plug this into our systems? Okay, let's build a prototype. Let's run it under Miri, right? All of this stuff happened before we actually started writing the code that we intend to merge. The second part is getting buy-in. My opinion, whether this is a reasonable idea to merge, doesn't matter. If I can't convince Ben, if I can't convince everybody else, because all of us are on the hook for this if it doesn't work, right? All of us are going to get woken up in the middle of the night if we're wrong about this. And so everybody needs to be on board with this being a desirable thing that we need to do that will work. So we have to get buy-in from each other. And here it's very, very important to not just be convinced that what we're trying to do will work, but also that those 17 steps of ceremony of actually nailing it down are necessary, that there isn't some easier, better way that we've already made. Because otherwise, why bother with unsafe if without having to bother with all of the risks of getting this entirely wrong? And so here, we used Codex to figure out if there are other ways. We used it as a thought partner. We used it to discuss what our alternatives are and why we think that they might or might not be possible. We also used it as a technical editor, because the net result of this step was a 2-page document that summarized what the problem is, what the landscape looks like, why we think we have an idea that will work, and why other things are not an option. And we wanted that document to be really tight. We didn't want to ship like a 17-page manifesto that somebody had to read, but it also had to get all of the details exactly right. Codex is very, very good at editing technical content, especially if you've already seen it with all of the prior reasoning about, how does this work? How is it de-risked? What is the prior art? What does the landscape look like? And the third thing is, we wanted to test all of the test cases with all of the crazy interleavings between all of those things that we had going on, all of the retries, and what if this request stalls, and what if it's a streaming request, and what if the other server recovers at exactly that moment. I can come up with a lot more test scenarios than I could reasonably write down by myself. And Codex on top of that managed to find a fair number of tests that we would have missed otherwise. I would much rather spend my time thinking about what things we should test rather than setting up a really complicated test harness that can get all of the complicated interleavings, all of the stateful futures, that deal with all of our scatter gather style streaming requests with retries in the loop and so on and so on. I could do that by hand, but I don't enjoy that. I'm not particularly fast at that. Codex is awesome at this. So I'm more than happy to hand off that part of the job entirely and just never worry about it ever again. And the most important part here is that if you've ever used Miri, Miri is a tool for finding undefined behavior that has snuck its way into your code. Miri can only find undefined behavior if you actually trigger the undefined behavior. You have to have a really high quality test suite. Well, guess what? We have a really high quality test suite. So when the test suite passed and Miri approved of it, we were actually very, very confident that our code was in very good shape. And, knock on wood, we haven't reverted it yet. It's been live for many, many months now, and we've trained some of our latest models on top of that code stack. So the bottom line is this. In Unsafe Rust, if you have a bug that reaches prod, it can very easily cost your team weeks to months to find out. One bug can take your entire team's quarterly roadmap and just chuck it out the window. The point of using Codex is not just to ship more code in less time. It also allows you to subject your work to 100 times more scrutiny than was ever previously feasible. This lets us ship faster because every time we don't ship a bug that sets us back by 3 months, it means that we've been able to spend those 3 months actually doing something productive. By not debugging, we are shipping faster. Thank you.